Hopefully, I'm telling you about the graph reconstruction conjecture. Nice conjecture, of course, unsolved, and a lot of, it's a constellation of problems, really. The questions you can ask yourself once you start down that path are really nice. So the idea is you're not given a full information. You've got partial information about something, and you want to know if you can get back the object you had at the start. If you take a graph, let's say, let me draw something random.
We're not looking at an X and a Y axis. This is a graph with the dots and the lines.
Exactly. We've got vertices, the dots, and the edges, the lines. This graph, I'm just going to butcher it a little bit. So it means I'm going to take each vertex and I'm going to remove it. So if I take this guy and I remove it, it means I'm going to take the edges that are connected to it while I go. So I remove this guy and I'm going to be left with these three guys. And I'm going to do that for every single vertex. So I take this guy out, and so this one remains on its own. If I take out that guy, this time it's easy, only this edge comes with him, so I'm left with a triangle. And finally, if I remove that one, then, well, these two edges come out, and I'm left with these three guys. So I've got things I'm going to call subgraphs, so they were part of the original graph. And now my question is, if I gave you these guys, knowing what I did with it to get them, can I get back to the original graph? And
like, can I take the jigsaw puzzle pieces and put them all back together?
Mm-hmm. So, I mean, the first thing you'd like to do is basically, what can I know about the original? If the original graph, if I'm only given these four things.
So I have been given the information that in each case, just one vertex was removed.
Exactly.
Right.
You know how these guys came to be. You just don't know where it comes from. Maybe I want to know. The first thing I can know is like, how many vertices in my original graph?
That must be easy to figure out.
Yeah. How would you do it?
Well, I would just count the number of vertices in the subgraph and add one.
Exactly. So actually, you got two ways to figure it out. So you've got, it's the number of vertices in the subgraphs plus one, as you say. Or, I mean, if I just, I'm going to call these guys cards. So I'm just going to draw a square around each of them.
Cards.
A square.
Yeah, you're calling them cards.
I'm calling them cards, and the full set of cards is going to be called a deck. This is going to be my deck of cards. I can also simply count the number of cards because I removed each vertex once, so I end up with like, this is the number of cards in the deck. So okay, I get back this information pretty easily, right? But clearly that's not going to be enough. I only know that my original graph has 4 vertices. Well, good for me, but not good enough.
Okay.
What else do you want to know about a graph when you're looking at it? What kind of easy information do you generally see?
I don't know if it's easy, but I'd want to know how many edges it's going to have.
I agree with you. I want to know how many edges I got. So how could you know about the number of edges? The thing is, every single time you remove a vertex, it comes with the edges that were attached to it.
And you don't know necessarily how many edges you lost to the process.
No, you don't. But what you know is that an edge, in my kind of graph, is always attached to 2 vertices. So it's going to be disappearing twice. Once, like this edge, this guy E, is going to be removed once when I take out this red vertex and once when I take out the black one. So if I count the total number of edges on all of my cards and I just do the sum, they're going to be like each edge is going to be counted a certain number of times. So I can just do the sum and divide by a certain number. And that number is the number of vertices minus 2, because there are 2 times where I did not get that edge. So that's an information that's pretty nice. I can just do the number of edges is equal to the sum of the edges on each card.
Like across all the cards.
Yeah, divided by the total number of vertices minus 2. So let's just have a look at what it means here. So we have 1, 2, 3, 4, 5, 6, 7, 8 edges in total if I add the number on each card.
Yeah.
And then each edge has been counted a certain number of times. It has been counted 4 minus 2 times in each case. So you just divide that total number by 2. So 1, 2, 3, 4, 5, 6, 7, 8 divided by 4 minus 2 equal 2. That means 4 edges in total, and that is exactly what's happening.
So this number of vertices in your equation means the number of vertices in the original
Exactly.
graph, not the number of vertices across all cards.
Exactly.
Yeah. Yeah.
So like 2 pieces of information I get back. Okay, is it enough? Again, so maybe in some cases it will, right? Maybe in that case we're like, okay, if I know there are 4 vertices and there are 4 edges and I know these guys should appear in my original graph, maybe it could be enough. But okay, I want a bit more than that. I want to have something a bit more systematic to go with.
Is that enough, by the way?
For this one,
It feels like with more complicated graphs it wouldn't be, but...
I think for this one it's probably enough.
Yeah.
I don't think because you've got this triangle and you know it has to be part of it. You know you're only missing one vertex and one edge. So if I take this guy, this is a subgraph.
Oh, of course, yeah, that gives it
So
all away.
I've got my triangle and I know I need to add one more vertex. So okay, let me add one vertex and one edge.
Yeah.
But there, I mean, if I connect, what do I connect my vertex to?
Yeah.
Either this guy or that guy or that guy, which is, I mean, it's always the same.
Yeah.
So, well, I've got my original graph, I'm happy.
So in this case, we could have done it. We could have done it with just that.
But this is it feels a bit like, okay, which card am I going to use? Then how do I start? I want to be a bit more systematic. So something I also like to know about a graph is the sequence of degrees. A degree of a vertex is the number of edges it is attached to. So that guy has degree 1. That guy, degree 3. This one, degree 2, and this one, degree 2. So if I get this, it means I know how many vertices, how many edges in total, and I know how many edges should be attached to each vertex. That's pretty neat. So if I can go that far, maybe that's already good. So I can go for the sequence of degrees, and that's easy because if I take a card and I'm like, okay, there's one missing vertex. That's my missing vertex. What is its degree? Well, I know that in total there should be 4 edges in my graph. Here there are only 2. This guy has to be of degree 2. It has to have the 2 missing edges. Here, the missing guy has to be of degree 3 because there's only 1 edge here. Here of degree 1 and here of degree 2. So I've got what is called the sequence of degrees.
But it feels to me here like if we had a really huge deck, like a huge graph and a huge deck of cards, you could still do this process that you've just shown me, but you would have no idea where they all were in relation to each other. Because when these graphs get really complicated, some of them are inside, some of them are outside. So is this enough? Are these 3 things enough?
Well, I haven't really told you the proper question, right, have I? I've just told you, can I get my original graph back? What I really want to know is, are there different graphs that this could be the deck of? The conjecture is about uniqueness up to isomorphism. So I want to know, like, if I give you that deck and I tell you, reconstruct the graph, please, do you get a unique graph? The conjecture is, given a deck of cards that belongs to a graph, can you reconstruct the original graph uniquely? So it's called the Reconstruction conjecture, and a graph is said to be reconstructible if this works. You can uniquely reconstruct it from the deck.
Just to answer the first question that you posed, which has become a trivial question now, is the answer, if I'm given a deck, I can reconstruct a graph? That the answer to that is yes.
It's still, I mean, I can reconstruct a graph, but we haven't been very clear on what a deck is, right? I've told you I get a deck doing this vertex removing operation. So actually the question you're asking is very nice because it leads to another question related to this, is if I just give you a bunch of subgraphs, how do you know it's a deck? Let's do an obvious one. If I just give you, these are going to be my cards. I give you this and this. Let me go up to 3 cards. Here's my deck. Is it the deck of a graph? Can you know? Like if we try to take these steps in order, we're like, how many vertices are there in my original graph? Well, judged by the number of cards, it should be 3, right? But then we also said it's supposed to be the number of vertices in each subgraph plus 1. So it should be 4, judging by that one, or 3, judging by that one, or 4, judging by that one.
Yeah, because a deck should always have the same number of vertices on each card, and this one doesn't.
It doesn't. So
Yeah.
I'm just showing you a very easy example of something that's called an illegitimate deck. This is not a deck of a graph. This is just some random, just like, okay, yeah, have a look at this. Can you play with it?
Yeah.
Well, you notice easy that you can't, but some of them are less obvious. I mean, I've got some cards here that we use to discuss the problem with classes or just as an outreach activity. And that guy, for example, is a fun example. Is a fun one of it's a fun non-deck. Meaning that if I try to do the 2 first steps, I'm going to get back something pretty clear. There are 5 cards and all the cards are 4 vertices. So that works. My original graph should have 5 vertices. I can do the same with the edges. I can sum the number of edges in each card. So I've got 3 plus 2, 5, plus 2, 7, plus 2, 9, plus 6, 15. 15 divided by 5 minus 2 is equal to, that's 3. So 15 divided by 3 means 5 edges in my original graph. And now I'm like, okay, well, now I can try to do the sequence of degrees and see if I get something. Well, that guy, how many edges does he have?
What, 6?
Yeah, 6. My original graph should only have 5 edges. Yeah, that's not a deck, that's an illegitimate deck again. It's a bit less obvious. We're not really looking for an algorithm, but if you want to try to reconstruct from a deck and you give a computer a way to do it and you tell them like, well, start from this, it's going to end up saying, well, that doesn't work. And why? So a related question to this conjecture, and I believe it is more studied by computer scientists, is this deck a legitimate deck? Does it give you back a graph?
And I'm imagining you can get massive decks. You can get thousands and thousands of...
Of course, the graphs that are of interest in a way are just, massive. But yeah, so that's a parallel problem in a way, and I think it's a very fun one, because at first you're like, yeah, well, you did this operation, you've got those nice cards, and you just get back a graph, and you're like, are these nice cards? Well, actually, ouch, no. So we went on the first tangent, and I love this problem because it seems to have so many tangent problems to it.
So my first question then is, if I have a deck and it's legitimate, I know it's legitimate, can I always reconstruct at least one graph? Can a reconstruction always be performed with a legitimate deck?
So I believe it is, and the question is only the uniqueness, but to be fair, I'm not an expert on the problem, and I've never been interested in the algorithm you actually use to reconstruct the graph.
Okay. Oh, well, okay. People can go and look that up.
Yeah.
But the question that is of interest, the burning question is each legitimate deck unique to one graph out there?
And so that, yeah.
And that's unknown.
That's unknown. I mean, it's known for certain what we call classes of graphs. So what I find fun about this conjecture, we generally say it's been stated in 57 by Kelly and in 60 by Ulam. So that's when it's been stated. And
hang on, twice? By two different... So how does...
kind of...
I thought first person gets it, don't they? Or is...
So that's the way it's generally stated when you look across the internet. What I found is that there's kind of, not a controversy, but you can probably find a forum where people are like, this is this guy who stated it first, this is that guy. But there's a first result related to the conjecture by Kelly in 57, and then maybe it grew up a bit more at that time. Again, people will be like, oh yeah, but I know exactly when this was stated. I don't. I just know that it's roughly the late 50s, and these two guys are definitely involved. This guy is really good with stating fun conjecture, and that guy proved some first results on the thing.
And what's happened since? Has any progress been made? Or?
A bit. So at the beginning, a bit quickly, yeah. Meaning you take certain classes of graphs and you're like, yeah, that should be easy for such graphs. One type of graph that is really easy is what we call a regular graph. This is a legitimate deck. And one thing you notice is, well, it's always the same one, right? First thing, like a deck, we didn't say it before, but it's a multi-set. You can have repeated objects. It's unlabeled. You just know that this subgraph is appearing 6 times in the deck.
Okay.
So it's always the same one. And if you do the number of edges, the number of vertices, you're going to notice that the sequence of degree is always the same. All your vertices have the same degree. And that's what we call a regular graph. You very easily deduce that information from the cards. So the first thing you know is, well, that graph must be regular.
When you say regular, what do you mean?
Always the same degree. So a graph is regular, means each vertex has the same degree. So if you look at the original graph, so you want to know how many vertices you have in total. You've got 6 cards, and therefore you have 6 vertices. And then you want to know the number of edges. And so you do 1, 2, 3, 4, 5, 6. 6 times 6, 36. And you divide by 6 minus 2, which is 4. So 36 divided by 4 is equal to 9. So the original graph should have 9 edges in total. And now it means that since on each of these cards you only have 6, the missing vertex should always have 3 edges attached to it. All of the vertices should have degree 3. That's what you get when you try to look at the sequence of degrees. It means that when you want to add a vertex to that guy, I want to add it here, it should have 3 edges attached to it. These 2 guys are already of degree 3, they're full, they're fully booked. You can only touch these 3 guys. Well, that's a good thing. You just connect it this way, and you've got your final graph. So all of these guys have degree 3. This is noticeable from the deck directly. You know it's regular of degree 3. And then when you try to reconstruct it, there is only one way. You take your vertex, you attach it this way. And that's very typical of the proofs that are known for this conjecture for certain classes of graphs. You first identify the class of the graph from the deck. We say the class is recognizable. And then knowing your graph is of this class, you can reconstruct it. So basically all these proofs, like most of the known proofs for classes of graphs, come in 2 steps. Step 1 is recognize the class. Example, like G is regular. And 2, reconstruct your original graph knowing its class. So the unique way to reconstruct it is this one. So that's what we did on the blue deck.
Do all regular graphs produce decks that are just full of duplicates?
Not necessarily. You could have, no. But if you take one good example is complete graphs, which like each vertex is connected to every single other vertex. And so when you take one, you're going to have always the same thing. But you can really, like doing the first steps we discussed, you can really easily get that, and then you get the second part. So it's nice and easy to have these 2 steps, but it also means that for some certain class of graphs, we don't know one of the 2 steps. Or we can only recognize the class, but we can't reconstruct the graph. So like the general results we have the conjecture there, it's almost nothing. We've got one lemma called Kelly's lemma, which states a more general results about subgraphs of the original graphs. And then you've got specific classes like, so regular graphs is a very easy proof. The trees, so these are the graphs that have no cycles inside them. So for example, that guy is a tree, but if I add this is not a tree anymore, there's a cycle. Trees are reconstructible, and that's a proof from...
Uniquely.
Yeah, uniquely, yeah. It fits, like, the conjecture is okay for the trees. It's okay for the regular graphs. But for many other types, we don't know. And these include classes of graphs that are very well known, such as planar graphs. The graphs when you can draw them without crossing over the edges.
Right.
And for these, we only know one of the 2 steps, for example. So it seems absurdly difficult. There is no general results for all graphs, and you've got so many classes of graphs. So what do you do when you have this kind of conjecture? And that's what really I found really fun with this problem. It's a friend of mine who just randomly came into my office and said, it's not his area of research either. It was just like, I just learned about this conjecture. Isn't this fun? And I was like, this is extremely fun. Let me please burrow myself into this rabbit hole for the next 2 weeks and I'll be very happy. And you're like, okay, well, why did we take vertices in the first place? Why don't we take edges? And then you can start stating a slightly different problem and see if it brings something to it.
So the fundamental question here is, when we run this one vertex algorithm that you showed me at the start, is there some fundamental information that is lost forever from at least some classes of graph?
It seems like there's not. Like the conjecture is... Well, I haven't stated the conjecture properly, have I? Because I don't even need to do it here, but if I just take these 2 cards, how many vertices should my original graph have?
2.
Yeah. How many edges?
Well, we don't know if there was an edge.
We don't know. Because, it could either be this guy or it could be that guy, right?
Oh, already there's one that's forever, we'll never know.
Yeah, so the conjecture is actually valid for graphs with at least 3 vertices. Because 2 vertices can have one edge that has been, the information is lost.
So 2 is a trivial example.
2 is a trivial example of something that doesn't work.
Yeah.
But have we found graphs that disprove the thing? Like graphs in general, what I consider to be a graph today was this kind of object where there are no multiple edges. I didn't let you try to have this kind of stuff. I also refused to have loops. So I considered some specific graphs, but still very, very, very large class of graphs. And then people went on, side quests again and said, but what could we do that could be different? Could we have a counterexample to the conjecture if we go a bit further?
Just one counterexample, just one deck that could be constructed 2 ways would ruin it forever.
Oh yeah, for the conjecture, one counterexample would ruin the conjecture. None has been found so far.
None.
But people have said, well, could we look at slightly different graphs? Do you know oriented graphs?
I've heard the term, but do you want another piece of paper?
Yes, please. Oriented graph is if I take my basic triangle, for example, and I put orientation on my edges.
Ah, right.
Well, this is an oriented graph. And for that type of graph, what they call digraphs, there's been infinite families of counterexample to the conjecture that has been found. If you take what they call a tournament, which is a complete oriented graph on 5 vertices, and you put orientation of the edges, you can actually find 2 different oriented graphs. There exists another graph oriented in a slightly different way that has the same deck as this one. And so they found counterexample. You can produce easy, low-degree counterexamples to the conjecture using slightly different type of objects. So, okay, that's one quest that was solved in a way. But then so many other questions that should maybe help you and in fact just create other new questions. You know, you remember that deck that has all the same images, like these are all the same cards. Do I really need all the cards? How many of them do I need to reconstruct? And that's another question you can ask. Is there a minimal number of cards?
Can you reconstruct from an incomplete deck? Hadn't even thought of that. Oh, you got my mind buzzing there.
Well, there are different type of questions you can ask. First one was like, you know that a deck is a multi-set. You can have multiple copies of the same card.
Duplicates.
Yeah. But what if you don't allow for a multi-set anymore and you only want one copy of each graph? If two subgraphs are isomorphic, you only take one of them. Can you still reconstruct for this? This is the set reconstruction problem. It's a problem that stemmed from this, but hasn't been solved either.
And do you need to be told one of these is a duplicate? Do you need to be told?
Good question. What do you impose on the problem, right? But the one I like is really this question of the number of cards, and we kind of turned it into a game. This is going to be it's a far-fetched game, but imagine I'm playing with you. I've got a deck, and you've got a deck. You created one, and the idea was we all have the same number of cards, but I want you to try to reconstruct the graph in a unique way, of course, because the conjecture has been checked for up to a certain number. I know this is going to work because we're not playing with 50,000 cards, but I want you to be as slow as possible. I want to win. So which cards should I give you? Like each turn I'm going to give you a card, you're going to give me a card. I'm like, this provides me with a bit of information, but I don't have enough yet. One card, I know I don't have enough. Two cards, I know I don't have enough because between the two missing vertices, there could be an edge or not, so I don't know. And then you give me your third card, I give you your third card, I'm like, now, is this enough?
That is a nerdy game.
It is a very nerdy game. But I mean, you know, game might be a bit of a stretch, but I've played it.
You have played it?
Yeah, of course I wanted to understand how it works. So I was like, what kind of graph could I draw that would be complicated to do in that way?
So you and your opponent sitting opposite each other with your decks, and also like pieces of paper and you're drawing and
Yeah, completely. And the question, the question is, what kind of graph is the hardest to reconstruct in this way? How many cards will you need? You want to have the maximum of cards needed. And one cool example is this guy. So the graph I'm taking is disconnected, meaning it is in two components. This is my full graph. This is G. It has two triangles. And now the cards from G, if you remove one vertex, I'm going to be left with this and this, right?
Okay, yeah.
But it's always the same. If I remove that guy, I'm going to be left with this and this, this guy, etc. So I've got this times 6. So I've got all identical cards. And the question is, how many will I need to give you so that you're sure this is actually the guy you want? How do you attack the problem? You reverse it. So you're like, if that's a card, what could I get back from it? So let's have a look. I start from here. So
Get
this
lots
is
of
my
things
guy.
back, couldn't you?
Yeah, I could have tons of things. So I know I have one extra vertex, right? So I could put my extra
Could just sit on
vertex.
its own. Could be on its own.
Yeah, it could be on its own. So that's a first possibility, right? That could be a guy. What else could I have? It could be this guy. But then it could be my original guy, of course, good news, right? But it could be several other things, lots of other things. And maybe I won't draw them all, but you can just ask yourself the question and go back and just like, okay. But so you've got plenty of possibilities. Yeah. And now, once you've done this, for each of the possibility, well, you go back to the original question, you draw their deck. And you see how many cards are exactly these ones. Of course, because the conjecture hasn't been, there is no counterexample known. You're not going to find one of these different graphs is not going to have exactly the same deck, or we would have solved the conjecture by the negative. That would be great, but no. But one of these guys has exactly 4 cards that are exactly the same as this one. So you know that 4 cards is not enough. You're going to need a 5th card that's going to make sure you have this.
There is a graph. This is true. There is a graph that produces
4 of these and
it.
2 other different cards.
Okay.
And so if I only give you the 4, you could not distinguish between my original graph and that graph I'm talking about. And so it is like, this is an extremal problem. Like what's the maximal number of cards I could give you without you being able to reconstruct it? But I could also ask, what's the minimal number of cards? So there's what we call an existential number and a universal number of cards. And this is another problem. And so all these kind of different problems, it's a constellation, and you're hoping that it will give you back some information that can help solve the actual conjecture. But so far, it's just, to me, who's not a specialist in the field and who's just like been browsing papers that come out, it looks like so far it's not giving back to the original problem. It's like more tangent stuff. It's pretty cool. I really like it.
So coloring graph means you want to color the vertices so that adjacent vertices get different colors. So for example, in this graph, I can color this blue and this green.
Until we get to term 600 and something. And at that point, Jake Sully says to the demon, "Fly straight, damn it."